Hi. Now we are going to deal with inverse matrix or inverted matrix A. This is how we are going to denote it. A to the power -1. This inverted matrix A or inverse A is the most fundamental matrix when it comes to solving systems of simultaneous equations. So, but before we learn actually how to build inverse matrix, let's discuss some of the properties of this matrix. Look, generally, why do we need inverse matrix? Because if we have an inverse matrix, then we will have that A times A to the power -1 and or A to the power -1, so inverted A times A will give us identity matrix. And this property, as you will see very shortly, is something that we need if we want to solve a system of simultaneous equations. Okay, now the first thing, we can find inverted matrix only for a square matrix. So A needs to be square, and look, it makes perfect sense because we require the multiplication from both sides needs to give us the same outcome. So it always needs to be defined. So we can say that only for square matrices. Okay, let's now list a couple other properties of square matrices. So first, not every square matrix has an inverse. So, what this is telling us is that if we have a square matrix A, we cannot be 100% sure that we will find an inverse. And again, this would be very closely related to systems of simultaneous equations that don't necessarily need to have one unique solution. And we will use this property very often a little bit later. Now, if matrix has an inverse, we say it's non-singular. And of course, if it does not have an inverse, we say it's singular. Okay, so now let's move to the second property, and this property is also very straightforward, and it says that A and inverse A are inverses of each other. In other words, if I'm gonna take matrix A in my matrix inverted A, and I'm gonna invert it, I'm gonna get matrix A. So those two are inverse to each other. And actually here we have one property that you're gonna that I was about to actually talk to you a little bit later, but it basically says that so if I'm going to take inverted matrix A and I'm going to invert it, I'm going to get matrix A. Now, another very straightforward to and Now, then there's another property that we should, that actually we can also deduce from everything we said thus far, but let's concentrate on this a little bit. So, if and if inverse matrix exists, it is unique. What does it mean unique? Well, it means that there is just one. So look, basically, if we had that some matrix A multiplied by some matrix B is the same as some matrix B multiplied by some matrix A, and if we multiply them, we get identity matrix, then from that we can get the B must be A inverse, and at the same time A must be B inverse. Now, let's prove it. Okay, let's just say that A and B are inverses of one another. So, now, we're going to make proof that if they are inverses of one another, of course, there's not going to be any other matrix that could be an inverse. Okay, so let's assume one more thing. Okay, let's assume, and we're going to assume that there exists a matrix C, that A times C equals to C times A equals to I. Okay, and now let's start with what we have over here. So we know that A times B equals to I. And look, what I'm going to do now is I'm going to pre-multiply both sides of this equation by C. So I'm getting CAB equals to CI. Okay, but what do we know from our assumptions? We know that C times A is equal to I, and we know that C times I is equal to C. Right? Now, I times B is equal to B, and we've got that B is equal to C. Okay, there's another way. There's another way in which we can. There's another thing. There's another way in which we could prove this, but I think this is enough. Just let's notice one more thing. If we've got the matrix BA, right, is equal to I, right? Again, with the properties that we have, what can we do with this equation? We can post multiply by A to the power negative 1. And look, what do we get now? We get B, A to the power negative 1, I times inverted A. And look, by definition, we know that this must be equal to I. And over here we get that this is A to the power negative 1. But B times I is B. So look, we clearly see that if B times A is giving us I, B must be equal to inverted matrix A. Okay, now, just to finish, please remember that we will have properties of inverses. So what are those properties? Well, first one we already discussed. If I'm going to take inverse, and I'm going to invert it, I'm going to get A. Then we've got that AB inverted is the same as B inverted times A inverted. And finally, the last one is the inverse of transpose is equal to transpose of an inverse. Okay, we will not be proving this because at this moment we don't even know how to get inverse of A, and we will learn it. But now let's go back for a second to systems of simultaneous equations and why inverted matrix A is so important. Okay, so look, now let's just say we have system of n simultaneous equations with n variables. So it looks like A11 x1 plus A12 x2 plus until A1n x A1 n xn. N is equal to some D1. Then we've got A21 x1 plus A22 x2 plus until A2n xn equals to D2. And we will have n equations like this. So the last one is going to be an1 x1 plus an2 x2 plus until an xn equals to dn. Okay, so now we already know that we can easily write this system into matrix notation, right? So we will get matrix of coefficients A11, A12 until A1n, A21, A22, A2n until An1, An2 until An. And then we will have vector of endogenous variables, so x1, x2, and xn, and vector of constant terms or vector of exogenous variables, d1, d2, dn. Now, what else we know? Look, we know that this is a matrix, this is a vector, this is a vector. This matrix is n by n. This vector is n by 1. But we already discussed this, that if I multiply this by this, I'm going to get a vector n by 1, which is of course equal to vector n by 1 over here. So now, if I can write it like this, why not write it in matrix notation? Right? We can write any system of n simultaneous equations with n variables in this form, where of course this is n by n, vector is n by 1, and this vector is n by 1 as well. So now, if I want to solve this system of simultaneous equations, I want to know what is the value of x1, x2 until xn. Now, how do I do it? I just need to solve this equation in matrix form. So first, what I would do is I would pre-multiply by inverted matrix A, right? What will I get then? A to the power -1 times A times x equals to A to the power -1 d. Now, A times inverted A times A gives us I, x. And now, I times x if I want to find the solution to a system of simultaneous equations, all I need to do is to find inverted matrix A and multiply it by vector D. And look, what will I get is a vector of solutions. And very important thing, from this moment on, please remember, we will be denoting every vector of solutions with asterisks. This comes from actually from economics, not from mathematics. And these asterisks are denoting equilibrium values, which we find using matrix algebra very often. And in our context of mathematics, we can say that it will be denoting solutions. Okay, so now we know that if we have inverted matrix A, we will be able to solve any system of simultaneous equations. But we also said that this inverted matrix A does not always exist. Well, let me explain why is it like that. And of course, I cannot give you an example of a system with n variables, of a system with n equations and n variables, because, well, that would be really hard to comprehend. But we can do just the same thing using two equations. But we will also use some knowledge that we gained, during our first class. And in the first class, one of our first subjects was linear function. So if we learned so much about it, why not use it now to understand better how these matrices, how these systems of simultaneous equations are working. Okay, so we will consider here three different types of situations we can encounter when it comes to linear equations. Okay, the first situation is when we have, let's say we have a system of simultaneous equations like this. Y minus ax equals to b, and y equal minus cx equals to some d. Right, look, this is how we see the system normally, right? But when we want to think about linear equations, this is actually the same as y equals ax plus b and y equals cx plus d. And look, let's assume a very simple thing over here. A is different than b, is different than c, is different than d. Of course, we don't need to have as many as, you know what? Actually, let's just do two assumptions. Like this. A is different than b, oh my god, sorry. A is different than c, and b is different than d. So look, we have here a system of simultaneous equations where we have two different coefficients and two different constants. Okay? Although those constants do not need to be different, I'll show you an example in a second. Look, how will we will be able to draw such a system, such two equations? Okay, let's assume they are both, that A and B are both positive. Or no, A and C, like let's just say that A is positive and C is negative. How will we see it? So, first equation, let's just say it looks like this. Where this point is B, right? If x is 0, then y is equal to b. Now, if c c is negative, we will have downward sloping line, and let's just say that it goes through some point D. Now, look, when we are solving this system of simultaneous equations, we want to find such specific value of y and x that it is true for this equation and for this equation. Where will we find it? Of course, at this particular point. So the point of their intersection. We will find some x and y that will represent the solution. But this is not the only possibility over here. Look, of course, if we would have that, for example, B and D are the same, then we would have our solution over here. But no, now look, even if the two lines have both positive coefficients but different from each other, we will always be able to find one unique solution. Okay, so we get that in such a scenario that we've introduced over here, where A and C are two different numbers, we will have one unique solution. How do we call this situation? We will call this non-singularity. Okay, but this is not the only possibility. Okay, look, the second possibility that we might encounter here is, what if we've got a system of two simultaneous equations like this. Let's just say we have y is equal to ax plus b, and then the second equation is cy equals to cax plus cb. Okay, now let's assume that a and b are positive, right? So if I want to draw this function, it will look like that. Here we will have b, right? Now, if I want to draw this function, look, we clearly see that this c here is unnecessary, right? We can divide both sides of this equation by c, and we will obtain the same equation. So look, if I would like to draw this equation, I will draw it like this. So, if I have a system of two simultaneous equations in this form, what does this imply? Well, this implies that we will have infinite number of solutions. Because look, when we solve a system of simultaneous equations, we want to find y and x that are true for both equations, that are fulfilled for both equations. In this case, any combination of x and y is giving us a solution that is fulfilled by both equations. So look, here we can say that we have a situation when we have only one unique solution. Here, on the other half, we have infinite number of solutions. Okay, so we've established that there's a case when there's only one unique solution, and actually this is the case that we like the most because it's really easy to handle and it's most useful in economics. This case, actually, as it turns out, for example, when we will be learning about differential equations, and especially system of simultaneous differential equations, you will see that actually we would like from time to time to have this situation. But there's also one situation we really don't like, and this is the situation when we have y equals ax plus b and y equals ax plus d. Look, what is so specific about this system of simultaneous equations? Look, it has, we see here that the coefficients on x are the same, just like here, but we will be assuming that b and d are some different numbers, right? So now, how could we graph this scenario? Well, here we could find that b, let's just say b and d are both positive. Okay, so let's just say that b is bigger than d. So here we would have a first function, and then here we would have the second function. Now, what can we say about these functions? For sure, well, they are parallel. How do we know this? Well, because they have the same coefficient of n. What is the main difference between those two functions? Well, the only difference between them is the constant. So look, basically over here I have exactly the same function, just a couple units lower. Will they have any common point? Well, no, they won't. And if they don't have any common point, this means that in this case we have no solutions. Okay, so now we see that we can actually distinguish three cases. One when we have one unique solution, one when we have infinite number of solutions, and one when we have no solutions. Definitely the third option is the most disliked. This one we will sometimes use, and this one we like very much. And now, if here we call this scenario with one unique solution non-singularity, as you might guess, those two cases that you see over here will be cases of singularity. And look, as it turns out, the procedure that allows us to find inverted matrix A will not only help us solve the system of simultaneous equations, but will also let us know in which of the two possible scenarios we are in. So, whether we are in non-singularity situation, so where we can find inverted matrix A, and then we can be sure that we will have just one unique solution, or if it turns out that we cannot find we cannot find inverted matrix A, it means that we have a singularity. If we have a singularity, it means we either gonna have an infinite number of solutions or no solutions. And look, as you might already notice, the key to the whole thing is in the matrix of coefficients. Look, we are looking for inversion of matrix of coefficients. And look, here we will have different numbers here, right? Over here. And notice that actually over here, we have some sort of repetition of the two equations in terms of coefficients in the coefficient matrix. Because here in coefficient matrix, we will have 1, 1, negative A, negative C, right? So we have two rows that are definitely different. But here, we would have 1A, 1A, repetition. 1A, 1A. Okay, so definitely we see that those situations have something in common, and this situation is clearly different, right? Now, so how can we be sure that we are in this situation and not in this situation? To this end, we need to learn about one more concept. This concept is called determinant and is a key to finding inverse of A. And this is the topic of our next video. Okay, thank you for your attention.